All right, so welcome to week 16, day 3. Today we're going to be talking a little bit about what goes into a machine learning model. So, as a background, have you guys have all seen the Titanic data set by now, right? So, does anyone want to take a stab at just summarizing what this data set is, why it's important, the stuff it includes, just in general terms?
But Omar, I can't say I've actually seen this data before because I went into Titanic um, site that Kaggle, I think it is. And I was looking through the site, watched some videos, but I didn't get to the point where I actually joined the competition. I think you have to join the competition to see this database now. Um, but I understand this data represents a guess, a guess based on certain criteria of, say, like gender, age, and I guess, and a few other factors. And it's gonna take a guess at the survivability.
That's pretty close. So this data is just data. It's just an Excel sheet. And this basically goes through and has all, I think it's 891. Oh, that's not what I wanted. Oh, okay. Well, let's go back to the preview. 891 passengers on board the Titanic. And it says this is a factual database that says who survived and who did not. It also adds in a bunch of other statistics. For example, it notes down here the class, if they were in first class, second class, third class, who they were, gender, age, some things about their ticket and how much they paid, their individual cabin, and a couple of other things. So there should be more info about this on the on Kaggle, but let's see, there might be something in the README here. Uh, Nope, these are all just other random data sets. Okay, so disregard them. But the point is that the Titanic data set provides a really good example for people to use quite often for something called binary classification. Have you guys heard this term before?
No.
Okay, so essentially, again, what machine learning does is it takes in a bunch of different parameters and it just draws patterns between them. And it can output results based on those patterns. In this case, let's say that we were interested in figuring out how to model the survival of people on board the Titanic. So, question we have is if I give you a passenger and I tell you their age, their gender, their ticket, their class, etc., but I don't tell you whether they survived or not, can you tell me how likely they are to survive? So the answer to that question is either is on a spectrum of they survived or they didn't survive. And you could say there is a 80% chance that so and so survived, or a 20% chance that so and so did not survive. Um, and that essentially is the core of a binary classification model. A binary classification model takes in a bunch of data and it says based on that data, this data represents object A or object B. So in this case, think about a machine learning model based on the Titanic data and basically reading through all of this data, figuring out general trends between, say, how does survival change as people get older? And what about how does survival change between males and females? How does survival change depending on your passenger class? And it ties all that together into a little model. And then you can test that model, and it'll give you a result of here's how many people survived, here's how many did not. Or here's which people survived and which ones did not, just based on general trends. Does that make sense? Any questions about that?
I have a question. The when you say you're like you have to like teach a model, are you assigning certain scores to say like gender or other categories, age, whatever, and then there's just a calculation. And because something like that it seems like you could just do in a spreadsheet. It doesn't seem like you need like a LLM for that. Or is the LLM actually making these predictions on its own?
So this is also where we draw a slight distinction between a machine learning model and a large language model. So the stuff that we will be developing in the next couple of days is your standard machine learning model. So now let me pull up the curriculum tab so I can show you what I'm talking about. So this is for today, building a binary learning model. And as you see here, it just classifies data in one of two categories. So this is not a chat GPT. This is not something that will, given a prompt, spin out a bunch of things. This is basically designing a function that takes in 5 inputs and outputs one thing, a yes or a no. The difference between a machine learning model like this and coming up with a spreadsheet calculation is the machine learning model should be more accurate than the spreadsheet calculation because it can figure this out, the sort of correlations in a near infinite number of dimensions. Like you can put in 30 different input variables that generate one output. And that's not an easy thing to do when you're modeling by hand using a spreadsheet. With machine learning, it becomes so much easier to do in order to solve that type of a problem. Does that help? Awesome.
Yes, thank
Any other questions? All right. So going back to that data, we have all of these other fields. So forget the passenger ID, but we have, all of these fields on top, except maybe name. And we want to figure out how those go to determine if a passenger has survived or not. So, all right, now this gets to the second part of your question, which is, all right, well, great, we have all this data. How can I do something with it? How can I bring it in and use it in order to make this model do what I want to and predict? So that is where, oh, wrong tab, switch back. That's where data set splitting comes in handy. So first off, I want to introduce you guys to something that I really like using for machine learning applications called Google Colab. So this is essentially, I know you guys have now been exposed to Jupyter Notebooks and VS Code and Anaconda. Google Colab is basically a Jupyter Notebook built into your browser. So you don't want to necessarily use Jupyter Notebook for a programming challenge or to develop a web application. But if you're just trying to play with a machine learning application or test some code very easily, quickly, and lightly, it's super easy to use. It's basically, you go to this website domain up here, colab.research.google.com. And if you're signed in with Google, you can just create a Python script that you can run, that you can run in your browser. So we're not going to get into the data and data processing today, which I believe that's a Saturday topic. But what I do want to just demonstrate is the way in which we use data for training and testing. So you'll notice here that I have these two CSV files that I'm reading in with PANS, which is a input, output, and data processing library. So the first CSV is a training CSV, and the second one is a testing CSV. Now, when we're usually dealing with data in a normal programming way, we just take in all the data at once. We don't care about differentiating between training and testing because what's the point of that? Your function needs to take in the maximal amount of data. And now it comes to a critical distinction between machine learning and normal coding. In normal coding, your algorithm does not change. Your algorithm stays fixed as one thing that you hard code, and that works. However, when you're working with machine learning, your algorithm should improve the more / the better data you give it. So it has a very dependent relationship on the data. You can also think about the need to split training and testing data, like teaching a 6-year-old how to do math problems. You need to make sure the training and testing data are different to ensure that the kid is actually learning. Otherwise, they're just memorizing answers. For example, if I train you, if I tell you all about how 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and we just stick to that example, and then I give you the question, what is 1 plus 3? You've already heard me tell you the answer, so you know the answer. That's different from being able to apply the skill of addition to a problem of, say, 2 plus 3. So that's kind of like the difference between training and testing. Training is like giving somebody, a very basic addition table or a multiple or their times tables. Testing is asking them a more difficult question to confirm how well they know the knowledge, or in this case, how well your algorithm can model the training data. So there's a couple of key things I want to point out here. The first one is that our training data is a lot larger than our testing data. And that makes sense. Again, go back to that learning analogy. People will read in college like a 600-page textbook for an entire semester in order to pass a 6-question test. Not the same concept, but relatively similar in machine learning. You always want to make sure that you are generally training your model more than you're testing it. Ooh, sorry about that. Excuse me. I'm going to grab a drink real quick. All right. The second thing is, if you take a look, can somebody tell me what dot shape means when I'm printing out something from pandas? Anyone have any ideas?
Yeah, well, it's just roughly the shape is like the I guess the format or size of the data, I guess, in
We can
in
make
sim
it even easier.
in the simplest terms.
It's the dimensions. It's the number of rows and then the number of columns. We have
Hmm.
891 rows in the training data and 12 columns. What are those columns? Let's check. We can print it out here. We see that we've got, the header, which basically just has the top of the data frame, and we see all the rows that we had before. Now with our testing data has less columns, or sorry, less rows, maybe half the number, but it only has 11 columns. What column might we be missing in the testing data? Any
Mm,
ideas?
pro yeah, probably the passenger ID, which is not necessarily needed.
That is a good intuition, and usually that would be removed when you clean the data set, which again, we're not going to do today.
Hmm.
But it is not passenger ID.
Mm. Mm. Is it the
So what
extra
is the statistic that we're trying to extract?
uh survives? So survives not in there.
Exactly. Because think about it. If survived was in the testing data, you're giving the model the answers, right? It's kind of like I teach you 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and then I'm going and telling you, all right, here's the test. 1 plus 3 equals question mark. But instead of a question mark, I'm just telling you 1 plus 3 is 4. It defeats the purpose of testing. So generally, your testing data will have fewer columns in it than your training data, generally, for that reason. So now we've got this data, and again, later on we'll discuss how to clean it up. But once your data is clean, or right now we can assume it is, we need to train the algorithm on our data so that it can model it. The way we do that is by setting up a neural network, which is what today's lecture is going to focus on. So I think on Tuesday you guys talked a little bit about tensors. Can someone tell me what a tensor is? like in your own words? What does a tensor mean to you? Anyone though?
Gotta be honest, I forgot.
Okay, that's all right. So a tensor is basically just an array or a list. It's just a more mathematical way of saying it. There are a couple of key differences, which is number one, that tensors are not, they're kind of come from within NumPy and PyTorch. For example, you can't really use a tensor in just like vanilla Python. Secondly, tensors also come with some benefits for accelerating your training and testing with GPUs and a couple other things. We don't need to talk about that tonight, but I just want to flag that. So again, a tensor, a list, an array, for our purposes right now in this context, they're pretty interchangeable. All right, so as you can see on the graph, we're taking in a bunch of tensors over here. Now those tensors represent the inputs to our model, right? So it's basically saying, hey, here are all of these different statistics. I want you to do some mumbo jumbo in the middle. So after that mumbo jumbo, I can tell you how all those statistics combine to say, is it group A or is it group B? Just for a binary classification model. Other models do different things. Right now, we're just talking binary classification. So given 15 different things, you, the model, need to understand how to tell if all these things indicate A or B. Now, the way that it does that is, again, by pattern recognition, which is what happens in these layers in the middle. So you can add or subtract as many layers as you want, but generally, you'd have two categories of layers. In general, you'll have your activation layer, which directly produces the output, and your hidden layers, which take the input and kind of manipulate them a little bit as you go. So for example, here, the input has three subarrays, right? Three tensors within the tensor. So we'll have, let's say, 3 nodes within our hidden layer. 1 node per input. Now we need to go from those 3 things in the input to 1 output. So to do that, we kind of step it down. So we'll say, all right, from the 3 things in my input, I want you to draw trends between them and kind of smush them together so that now we only have 2 outputs from the 3, which is going to be the second hidden layer. And then we can go from 2 to 1. And then once we're up to 1, oh, that's our output. Send that out. So again, we have a couple of different layers. We already talked about the input layer. Again, the hidden layers are where the model learns to recognize patterns. Excuse me, sorry. And then the activation layer is kind of like the last step before you put out the output. So this discussion for today is going to be mostly theoretical because you guys will not have all the tools you need to play with machine learning models tonight, but this is good preparation for when you have to do that. So again, as we mentioned, we're going to be using PyTorch, and then PyTorch will be used specifically to build our neural networks. So we have a couple of different layers that we can use. Generally, people will use a linear transformation in the hidden layers, and then a sigmoid transformation on the activation layers. So why might we want to use a linear transformation? Well, they're not super computationally intensive a lot of times. They're good at modeling simple relationships, but they're not great when modeling really complicated systems. That's where the other layer comes in, which we put all the way at the end, which is the sigmoid layer, which, as it says on the slide, it will basically take your data input and map it to something between a 0 and a 1. In our case, going between a 0 and a 1 is basically the difference between life and death. So if your model returns, let's say a 0 is dead, 1 is alive. If I pass my model 12 inputs that are, or 11 inputs that are relevant to a person who I want to figure out what their chance of survival is on the Titanic, and let's say I get out 0.65 from my model. That 0.65 from my sigmoid is going to tell me there's a 65% chance of their survival and a 35% chance that they die. So we'll skip through some of the math stuff. Again, over here is now where you can see a little bit of how the model will look when you actually create it. So break it down. NN.sequential basically just sets up the number of layers. So NN sequential will basically tell PyTorch, hey, I'm creating a thing that is going to house all of this stuff, all the hidden and activation layers. So the first thing I'm telling you, whenever you set up a model like this and you input a layer, whenever you type a layer out, you need to say the number of input nodes or the number of inputs going in and the number of outputs coming out of the model. That is what defines your layer. So for example, in our input here, we have 1, 2, 3 things going in, and then just 1, 2 things that we want to go out. So 3 input, 2 output. So we can just write that up really easily right here. 3 going in, 2 going out. You always want to make sure when you're defining your model that the number of nodes going out of one layer is the same as the number of nodes going into another. So again, you can't really do something like 10 to 5 and 2 to 1. You need to be 10 to 5, 5 to 2, 2 to 1. And then at the end, we're just adding sigmoid just to wrap everything up nicely in a binary classification scheme. All right, we talked a little bit about this. Feeding data to the model. So again, this should be a relatively familiar format to you guys now. This is just what a PyTorch tensor looks like, which is pretty similar to everything we've dealt with before in terms of lists and arrays. You'll want to make sure that your tensors contain sublists. That's very important. Yep, and then down here, the way that you actually input your tensor into, aka your data, into the model is just like calling a normal function. No real differences. All right, so any questions on this before we get to weights and biases? I know we kind of talked through a lot, and it is a little hand-wavy. But it'll get a lot easier once you guys are able to process data and create your own models, which I wish we were doing tonight, but unfortunately we're not. Okay. Yes, Art, go ahead.
I may have missed it, so I apologize. But when we're talking about data that we want to input, and we're talking about age, and gender and stuff like that, how does that get translated into these arrays of like 1, comma 1, comma 1, comma? I mean, how does that get translated to so we know that male represents 1 dash 1 dash 1 or comma 1? How does that get translated?
So that comes down to something called basically data preparation, which is what we'll talk about that probably on Saturday. So I just flipped it back to my my Jupyter notebook here with our data, right? So we can see here that, like, for example, male and female, those are not floats, right? Those are strings. Um, we've got the cabin, that's also a string. Um, You've got this embarked thing, which is a string, but everything else, like the survived or the peak class or the age, those are all numbers. So the first thing that we need to do when we're trying to figure out how to make our data ingestible by the model is we need to figure out how to turn those strings into some sort of number. It could be as easy as saying male is 0, female is 1. It could be as simple as saying, cabin, like the C85, we'll change it to 085. And then let's say there's a B85, that changes to like a 185 or something like that. But that's a responsibility of the data scientist who is either giving you that data, or if you're the data scientist, that should be your responsibility to figure out how to best input that for the model. Yeah, really good question. Any others from anyone else?
I have one more question in mind.
Yeah, go for it. This is also, I can go on about this stuff for a while. So please feel free to ask questions. This is one of my favorite things to talk about in all of programming.
Yeah. I think it was Tiffany said this is your baby. This is the thing that you enjoy. But I'm curious to know if there's any type of program like Mockaroo where we can say, hey, take this data and give me back some filtered data that can be adjustable by the model.
Does this help?
Very
So
cool.
this is actually also kind of a cool thing that you can do. You can use a machine learning model or an LLM to generate data for your machine learning models. It's like Inception, but AI Inception. Um, I personally am a huge fan of using tools like Mockaroo or honestly ChatGPT is great for generating your testing data sets. Or just generating data for you to mess around with your model. I would not train it on ChatGPT generated data because that should be using real data, but for testing, absolutely, it's helpful. Any other questions on the data sets before we get back to the models themselves? All right. So again, we kind of so would anyone like to explain what this piece of code is doing based on what we talked about? So what are each of these layers?
Yeah, so your your input layer there basically so it's got three three columns and two rows. Uh, I'm sorry, uh, three rows and two columns. And so you got three pieces of data that you're using there, and the hidden layer is taking only two rows and one column of that data, and is condensing it down to two columns and one row, and then that sigmoid is the activation layer that's going to output uh, just um, one thing for you, or one result for you.
So that's close. So I'll let me go emphasize that. Okay, well that's not in here. So when you do a dot shape for a data frame, that dot shape gives you the number of rows and the number of columns. The number of rows, go back to this, the number of rows in here, 891, is the number of data points that you are going to analyze. The number of columns is the number of variables that you have. So when I'm going and creating a classification model like this, I don't necessarily care about the number of data points I have. I care about what's in those data points. So if I have 1,000 data points, but each of those data points has 4 things associated with it, like name, age, zip code, and if they have a dog. Those are the 4 things I care about. Then I'm going to create my first layer is going to have 4 nodes in it. Because my input has 4 things. And I want to make sure each of those 4 things gets passed into my model. However, my output is going to be one thing. My output is going to be whether they also wear glasses or not. I don't know, something like that. So how do we go from 4 things to one thing? Or in this case, 3 things. So first, I can't go from 4 to 1 immediately. I have to kind of take small steps. So we go from the 4 things maybe to 2 things. And that is where each of these layers come in handy. The layers kind of act like little steps in order to get patterns across your data. So this first layer here is going from your input, which has 3 selectors or 3 variables, and it's taking it down to a hidden layer with 2 variables. And then the next one is a hidden layer that's taking in the 2 variables from the last layer, and it's combining both of those into one. And then you're outputting that one final variable. Does that help explain the model a little bit more?
Yeah.
Yeah, Art, go for it.
What are the constraints? Like, let's say you started out with 15 variables. Can you go like down to 10 and then down to 5? Or I thought you had to go one step at a time. So what are the constraints?
So it really depends on what you're trying to do. If you try to go way too quickly from 15 things to one thing, you will probably lose a good amount in the process. Again, think about this like teaching somebody a skill. So I'll give an example. If you're teaching somebody how to drive, they need to know how to work the gas, the brake, the clutch if it's an older car, the turn signals, the steering wheel, and check all the mirrors. Imagine I gave somebody who's never driven a car all of that and said, "Go drive me on the highway." They're gonna be freaking out and panicking because they're not going to know which things to look at more, how to prioritize, or how to use any of them. That's kind of similar to what happens if you tell your AI model, hey, go from 15 things down to 1 immediately. In contrast, let's say you start out by telling, your learner, all right, for right now, just focus on steering the car. Like just like the gas and the brake and the steering wheel. I'll do everything else. I'll look out for the traffic. I'll tell you when to stop and go. But like you're breaking it down and making it more manageable. And then as they get better at it, you then give them, more independence and more freedom. It's kind of similar in machine learning, where again, you can't go from 15 things to one thing, but you can go from 15 things maybe down to 12. And then from 12 you go to 10, and then from 10 to 6, and so on. So there are ways to measure, because you can't really theorize too well about, hey, I have X number of inputs, how many layers, and how many, what is the pass through between those nodes. Determining that is usually something that you have to do by playing with your model. So, for example, you might find that the first time you do this, you have 3 layers, and then your model ends up being terrible. So you're like, okay, my model is not trained well on the data at all. So I'm going to increase the number of layers up to 5 so that my data has a little bit more time to bake. And then hopefully it works. And then sometimes it doesn't. And you just kind of keep changing it based on that. Any other questions? All right. So we talked a little bit about the sequential model. And again, you guys already talked about tensors. We're not going to talk about that too much now. The one thing I'd like you guys to note is, again, this model is this and this chart are identical. The only difference is the model equals that works in order to, crack your data and generate your predictions. This is just a diagram. Now, they're exactly the same thing. Now, a better way to think about machine learning algorithms is they are a black box. Think about it, given 15 different things. I need you to generate one thing. How you do it is up to you. To me, that sounds a lot like a function, right? Given 15 inputs, generate one output. It's an input into a black box and gives you an output. Machine learning is the same thing. You are essentially designing a very fancy function. So it makes sense that when you are testing your machine learning model, you're testing it or running it on your inputs as a input to a function. Right? Again, like this format down here at the bottom, that's your standard. I have a function, I'm putting in some inputs, I'm getting an output. And that is the usual format for how you're going to bring in your results from machine learning. There are a couple of other things that are important. Let's go back to the Titanic example. So again, we are going to be inputting all of these different things into our model in order to determine if a passenger has survived or not. So let's say in the course of doing so, we just give our model all 12 things, or all 12 variables, and we tell it, learn correlations between them. Let's say our model discovers that there is a very well-defined relationship between age and survival. As you get older, your chances of surviving go down, hypothetically. However, there is not a very good relationship between male versus female survival. So, this is a question I pose to everyone here. Let's forget all the other variables and just focus on age and sex. If I now, with the information that you now know, that age is correlated with survival very strongly, and gender is not, if I give you somebody's age and somebody's gender, and I tell you, did they survive, and I ask you, did they survive or not? Are you going to base your conclusion more off of their age or off of their gender?
Age.
Exactly. That is exactly what your machine learning model is going to do as well. So let's see, where did that go? Weights and biases. Perfect. So essentially, your machine learning model will look back while it's learning and training and saying, hey, it's interesting that gender doesn't really affect us that much. So the next time I analyze this data, because I'm going to analyze it multiple times, just like you have to read a book multiple times in order to really understand it. I'm going to gloss over the gender part a little bit, and I'm going to focus a little bit more on the age part when I write my function. That's basically what weights and biases do. You can adjust those as a programmer as well. Let's say that the machine learning model thinks that, oh, gender doesn't really matter. But as a researcher, you know that it does. You can tell your model to correct for that if you have to. But again, it's not always required. So as it says here, so weights connect your neurons between each other. And again, the neurons or nodes in your model are these sort of things that pass data forward. So your weights will affect how things get propagated through the model. Let's see, first and second layer weights. This is a lot of detail, and we don't really need to talk about that too much right now. But yeah, so the important thing is here. I think this is a good formula to keep in mind. So the way that weights and biases work is that you take your input and then you're going to multiply that by the weights. So think about the weights as kind of like getting like a 2x or a 3x bonus in a video game, or you get a debuff and then you're only getting like half. That's kind of like what weights do, is for each of the variables you input, it will just multiply them by some factor, depending on how important they are or not. After you multiply, then you're going to add the biases. Think of a bias kind of like a golf handicap. Like it'll offset your training and your outputs. So like weights are kind of used to amplify one thing over the other. Biases are used to kind of create a fixed difference between different parameters. So does that make sense? Are there any questions about that? Again, I know it is very abstract, but it gets a lot easier to understand once you guys actually start creating your own models, which again should be very simple. So right now, we're kind of doing a lot of this at a theoretical discussion level. So ask questions if you have them. All right. So if there's no questions, let's recap. Adam, what is a binary learning model?
A
Don't look at the screen.
binary learning model, is it?
Yes.
I think heard you talking about how it's not the same as I think I'm thinking about the language model, and no, I'm thinking of something else. Never mind.
All good. You want to retry it?
I'm trying not to look at the curriculum right now, just from memory.
So what was the
it-
goal of the Titanic machine learning thing that we were talking about today?
The goal was to categorize data by things that were most likely to happen, I guess, or try to predict what was who was most likely to survive. Sorry.
Exactly. Yep. So again, it's predicting will someone survive or not survive? If we think about how that's recorded in data, that's saying, is this person a 0, aka dead, or a 1, aka alive? Zeros and ones, that's binary. And that's what a binary classification or a binary learning model is. It takes a bunch of inputs and it smushes them into something representing a 0 or something representing a 1. So, all right. So, Art, can you talk me through this diagram a little bit?
Sure. On your left, you're going to have all of your data represented in a binary format. And I have filter stuck in my head. So you're going to pass it through the first hidden layer, and it's going to get filtered out. And based on certain relationships, instead of the next layer, you're going to consolidate that or filter that down to 2. And in this example here, there's only 2 hidden layers. So by the time you get to the activation layer, that is pretty much going to be your final output. And that's just going to convert it to your to something that's that we can understand in the output section.
Perfect. Yep. Good. That was a good explanation. I don't really have too much to add there. Nicely done. And then lastly, Cisco, can you talk to me a little bit about where weights and biases fit into this picture?
Well, well, I actually have a question as far as before I answer that.
Please, yeah, go for it.
With the so with this model type, is it fair to say that, say our inputs are, say we have 6 inputs, right, instead of 3, we start out with 6. Is it fair to say that we want to create the hidden layers or have the hidden layers that go from taking it from 6, 5, 4, 3, 2, 1? Or I mean, it could be 6, 4, 3, 2, 1, or something like that, like you were kind of stating earlier. But wouldn't it be more efficient to actually have 5 hidden layers in between the input and the activation layer? Strip, that basically condenses it down, the I guess n-1 layers, hidden layers, before you get to your output. Is that about right?
So that is in general the maximum number that you want to have. So for something with 6 inputs,
Mm-hmm.
that's not too bad. You can pretty easily go from 6 to 5 to 4 to 3 to 2 to 1.
Mm-hmm.
Let's say you have a data set with 32 inputs
Okay.
and you need it to generate 1 output.
Right.
You do not want to have 30 layers in between.
I see.
Because
Okay.
if you have a giant data set,
Mm-hmm.
that's going to be a ton of training time. And that uses up valuable computing resources.
I see. Okay.
So, in general, I usually like to keep it to no more than maybe 5 layers in general.
Okay.
Um, but the only way to really figure out the right number is to
Mm-hmm.
play with it. Change the
Okay.
number of change the number of hidden layers. Change the relative number of nodes going into and out of each hidden layer. Like that's the only way that you can really figure it out concretely. I mean, there are like formulas or tools that you can use as guides, but at the end of the day, it comes down to. Now, I believe we'll talk about this when we start talking about like efficiency.
Mm-hmm.
But that's what it comes down to. Also, you
Okay.
can overtrain sometimes, but that's a different problem entirely. But that can be related.
Okay. Okay. All right. So weights and biases. So the weights and biases, basically the 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 weights are used to give a certain level of to help the model uh give a certain level of importance, I guess, to the data, to certain pieces of data over others. And I guess the biases will kind of like it's something that the model itself learns over time or has its own it creates its own biases based off of the data sets that you have and the ones that are the pieces of data that it finds
No, that's exactly correct.
yeah.
The one thing I will mention, usually people will think about weights and biases together. Like you will very rarely hear people say, "Oh, the model's weights, da 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 da, and the biases."
Mm-hmm.
Like they're a package deal. Like
Okay.
they always go together. So the industry standard term, and I should have mentioned this before, is just weights and biases.
Okay.
Now, it's good to break them down separately in your head when you're at the learning stage,
Mm-hmm.
but when you're actually doing this, usually what you'll do is you'll run the model on your data. You'll see what types of weights and biases it generates on its own,
Mm-hmm.
and then you can also go in to manually correct or set the weights and biases.
Mm.
So otherwise, the model does it on its own. Like it has
Okay.
that ability.
Okay.
Yeah, that was a pretty good explanation.
All right.
So talked about what a learning model is. We talked about what neural networks are. We talked a little bit here about what the layers do and how they work. We talked about input tensors. Again, know that when you create a model, it's the model is layers that are networked. So make sure that you keep track of how many nodes are in each layer and making sure it kind of all trickles down to one at the end with that sigmoid. And a model is a function at the end of the day. It takes in a tensors as inputs and it spits out an output. And then again, weights and biases are something that are generated during the training process of your model. You can set those in the back end as well, but you really don't have to. And then the last part that I think this sort of talks about a little bit is you don't have to use the built-in sequential method to build a model. You can also build your own just as a normal Python class. However, this is only really for complex models. My personal experience, you don't really need to define your own model in most use cases that you guys will end up running into for now. Later on, maybe, if your models are inadequate. But in order to determine if your models are inadequate, you first need to be able to learn how to assess your model, which is something that we'll most likely be discussing next Monday. So with that, that's about it for class today. You guys have any questions, comments, concerns for me at present?
No, I don't think we do. Well, I don't think I do. I'm sorry. Speak for
All right.